Hey, it's Kley. Welcome to another video. This is going to be a circuit overview and breakdown of the Big Muff Pi. This is near and dear to my heart. It's actually the first effects pedal I ever purchased. And I pulled up this gem of a video from 10 years ago, and this thing is cringy. Oh man, I've got like this crazy Minnesotan accent, yeah, and it is pretty insane. So feel free to check this out for your viewing pleasure. It's not actually a good video, but I do think it's entertaining in a cringy way. But what I really want to do today is I'm going to embark upon a Big Muff Pi build. I've been working with my friends at DIYguitarpedals.com.au, and Erik has been really awesome. He sent me this kit, and we've been chatting, and he's just a great guy, and they've got an excellent YouTube channel and website. If you're into making pedals, learning more about it, please check them out. And what I want to do is, starting off, I want to look through the schematic and see if I can understand the circuit a little bit better and discuss any modifications that I want to use. This pedal is fascinating because it's so old, and so there's a lot of different versions of this pedal that have existed throughout the years. I'm not going to necessarily do a super deep dive, but I am going to try and highlight, I think, where some of the changes can occur, because this pedal definitely can morph, and there's a lot of little places where you can make changes, and that's where all the different versions come from. But yeah, so let's just go ahead and get started. And this is kind of a breakdown of the schematic, and it's kind of highlighted. This is from Electro. That's a great website. Go check it out for more information. And this is a great breakdown, I think, of what's going on in the circuit. So let's go ahead and take a look here and just start walking through. Now, from a bird's eye perspective, I want to highlight that there are 4 transistors. There's one here, there's one here, there's one here, and there's one here. And I think those 4 transistors are important, and they really help to define the sound. Now, a transistor, you want to think of it as a gain stage. So it's really all it's doing is amplifying the signal. Now, there are other ways you can use a transistor, like as a buffer to change impedances, but in this situation, every single one of these transistors, you got signal coming in. This is called the base, and it's exiting through the collector. And then you've got the emitter down here, which is grounded, and that's going to help bias the transistor. But every single one comes in the emitter and leaves through the collector. So that's just being used as kind of a typical, I believe it's called a common emitter amplifier setup. And so let's go ahead and take a further look. We've got these 4 gain stages. Now, just to kind of give a little bit of context on that, 4 gain stages is quite a lot in terms of a distortion pedal. If you think about something like an LPB1 booster or an MXR micro amp, those are kind of your simple 1 gain stage boosts. You can put some clipping on that and you get like an electro distortion or a more simple type distortion. If you go to something like a fuzz face, you're going to have 2 transistors, or later other fuzzes maybe have 3 transistors, like the tone bender. And then you've also got, other drive and distortion pedals like the tube screamer. Now that I think I'll have probably 2 gain stages, but then it'll also have some buffers, just the way that pedal was built. So 4 gain stages actually amplifying the signal is quite a lot, and is probably one of the most amount of gain stages that you would see in a distortion, overdrive, or fuzz pedal. So that's kind of an interesting note to start with. Next, I think that it's important to note that this input booster and the output booster are very similar to one another. And then also these 2 clipping gain stages here in the middle are also very similar to one another. And so basically you've got the boosters are just helping to raise the input level so that the rest of the pedal functions a little bit better. But I'd say the tone shaping more happens here in the clipping amplifier. And then the tone stage here is that tone control. And that's, I think, also a huge characteristic of this pedal's sound, which we'll get to in a minute. So let's just start here at the beginning. Okay, so we've got our input jack. We run into a 39K resistor. This is going to help to impede some of that signal and provide some input impedance. Overall, it's kind of a low impedance input, but I think if you read through the article on Electro Smash, they argue that it doesn't really matter so much because there's so many subsequent gain stages that it kind of makes up for that, which is interesting because I think other pedals like the fuzz face is known for having a low input impedance, which means it's very sensitive to what you put in front of it. But the Big Muff kind of gets away with that simply by just kind of overpowering the signal. You know, I think that's characteristic of the Big Muff, that it doesn't really matter kind of what else is going on. It's such a dominant piece of your signal path. And so just kind of an interesting note here on the input impedance. Then we run into this C1, 1 microfarad. This is I'm going to call it a coupling capacitor. When I refer to coupling, there are actually similar of these all throughout the circuit. There's one here at C5, there's another one here at C13, and there's another one here, I think this is 30 maybe, and even another one here at C2. So all these capacitors, coupling, what that refers to is it decouples the two signals. And when I refer to two signals, this is kind of a weird thing that I had to kind of wrap my mind around, but oftentimes in electronics, you have situations where you have two signals running through the same wire. You have an alternating current, which goes like this. That's your sine wave. That's like what your guitar produces, or something from a stereo, an audio signal that has a frequency or a tone. That's going to be an alternating current signal. And then you've got a direct current signal, which is just like a solid block. And that's like what's coming from your power supply. So you have 9 volts of direct current that's coming down on this resistor, and that's powering the transistor. But you've also got your millivolts of alternating current coming from your guitar pickup. And those are both kind of in this part of the circuit simultaneously, which is a very strange thing. They don't necessarily interact with one another because they are so different, direct versus alternating. Well, the problem with that is that if this direct current were allowed to continue to go backwards in this direction, that would cause a lot of problems. You would have DC going into your guitar pickups, and you know, if you've ever licked a battery, you know, that's contacting 9 volts of direct current, and you're not going to really like that little shock. So the coupler here helps to preserve some of that. So, and this capacitor actually blocks direct current, and it selectively allows alternating current to pass based upon a frequency. So the direct current that comes into the signal from the power supply is blocked from continuing to go this way, which is a good feature that you want. And that happens all throughout the amplifier, that decoupling effect. But then it also, like I said, affects the alternating current based on frequency. So with capacitors, typically the larger the value of capacitor, imagine if this was like a 22 or even 100 microfarad microfarad capacitor, that would be a very large value. What that means is, if you think about if this is a frequency, right, we've got 20 hertz, that's the lowest signal a human being can hear, and this is 20K, that's the highest, like a dog whistle or something. The value of this helps to determine a low or a high pass filter, because it's going to work in conjunction with this resistor here. You've got a resistor and a capacitor, an RC filter. So the value of this helps to determine where on this audio spectrum it is. So for example, if you use like a 100 microfarad capacitor, this frequency point right here where it starts to curve, that might be at like 10 hertz or 50 hertz. And I don't know the math specifically, but basically as you lower that value, so if we've got 20 UF is going to make it very low. And if you go over here to like 0.001, what that's going to do is it's going to take this curve and move it this direction. So it might be here or it might be here. So basically what that means for your effects pedal is if you want more low end, all of these coupling capacitors are a place where you can change that. So if you would increase this value to like I said, 20 microfarad or 100 microfarad. That would help to increase low end. So this is, I believe 100 NF is 0.1 UF. So if you would increase that to like 5 or 20, same thing here. So this is a spot where you could increase bass by making these smaller, or making these larger. And then conversely, if you want to cut away some low end, make the low end more tight, make the mid-range and high end more pronounced, you could even go to a 0.01, and that will help to trim some bass. So all of these coupling capacitors are places where you can tone shape and help to control the amount of low end that you've got in the signal all throughout. Okay, moving on, I'm going to highlight R9 and R14, these two resistors here. When we talk about being a common emitter, this helps to bias the resistor via the base. So what they do is you've got 9 volts of direct current coming in from right here, coming down this, hitting a little bit of resistance here, and then using this 470K and this 47K, it forms a voltage divider. So that means that the voltage is going to be divided, and some amount of it is going to go this way, and some amount of it is going to go this way. So based upon these values, because we have a larger value here and a smaller value here, it's not going to divide it up too heavily, but it will divide some of the voltage, and that divide is going to help to bias this transistor. And that bias, when you think of bias, you want to think of it in terms of like a governor on a golf cart, right? You've got, basically, if the golf cart is running at full speed, it's got a governor, so it's not allowed to run too fast so that you don't get out of control. So that's what these resistors do. Similarly with R22, this is coming off of the collector, so it's providing a little bit of resistance on the collector, again to help control and bias the signal. And really with these three resistor values here, I would say that in combination they all help to serve to set the bias. So you can tweak that in subtle ways to change the gain or the output of the transistor. I've seen some circuits that don't have any resistance here at the collector, so that's really going to run it a little bit hotter. And even a higher value would help to clean it up a little bit more, so it would be less kind of wild and crazy and loose and out of control. So these are little resistor values you can tweak to change the performance of the transistors. And again, these are pretty similar all throughout the circuit, maybe with some subtle changes, 470 and 100 instead of 47, 150 ohms instead of 100. And some of this too is very much going to depend on the type of transistor that you're using. So if you're using, this one's calling for a BC239, if you're instead using like a 2N3904 or a BC109 or a PMP germanium, these biasing values are going to change. So you should kind of take a look at what transistors you're using and use the recommended biasing values for that transistor. Okay, now I want to talk about these two components right here. Like I said before, the signal comes into our transistor, goes this way, gets amplified, and exits through the collector. Now when it hits this point, obviously the signal will continue to go this direction. It'll hit another coupling capacitor here that I forgot to underline. But what I really want to highlight is that when it gets to this position, it actually has opportunity to go back this way. That's called negative feedback. Negative meaning it's going backwards. And feedback, like I said, it's feeding back into its prior position. Now, negative feedback on an amplifier stage is used pretty much, it's here at Q4, this first transistor. It's used again here, Q3. It's used again here, Q2. And then it is not actually used here on this last Q1. So what negative feedback does is it helps to stabilize the amplifier. It helps it to perform more consistently. So, the Big Muff is not known to be subject to inconsistent. It's a very stable fuzz. And I think that this is part of that. It also helps to flatten the frequency response so that it is more even. There's going to be more bass, more treble, and more of an even mid-range. So again, this is a technique that's used in like hi-fi, whereas a direct signal tends to be a little bit more raw and mid-range pronounced. So this contributes to some of that more mid-cut because this negative feedback helps to stabilize the frequency response. And the other thing it does that is interesting is you've got this resistor here, but you've also got a capacitor. Now this is a small 470 picofarad is a small value capacitor. So what happens is the signal reaches this point, and capacitor will selectively attenuate signals. So with this 470 picofarad, again, think of our frequency response here. 470 picofarad is a low value. So as I said, if this is 20, this is 20K, this might be up here at like 1K or 2K. I'm not exactly sure where. But basically what this is going to do is it's going to say frequencies that are above the cutoff point are allowed to freely negative feedback, whereas the rest of these frequencies in this range have to go through this resistor. And it's a larger value, 470K, so they're going to be resisted by a meaningful amount compared to the capacitor, the higher value frequencies, which bypass frequently. So what that's going to do is, with a negative feedback loop, you want to think of it as opposite, meaning frequencies that freely negative feedback are going to be suppressed, because when you run through here, you get amplified, but then you go right back through. You kind of see the carbon copy of your former self, and it serves to kind of negate or cross out one another. And so what this is basically going to do is attenuate or bring down these high frequencies are going to go down. So you're going to cut treble. Now this is really interesting to me because of what I was looking at in the last couple of weeks. When you have a ton of harmonic distortion, there's another video on my channel if you want to check it out. But what that basically does is, let's say you produce a tone that's like right here at, let's say 300 hertz. Well, when you clip it and distort it, which is what we're going to do coming up shortly, you're going to create, so if you add one signal here, you're going to create all these additional harmonics that are going to come up above. So it's interesting that you, by attenuating the bass signal at 1 or 2K, which is a relatively mid-range proportion, so we don't have a lot of treble. So really a lot of the high-end treble content is just simply coming from clipping the signal and not actually coming from the bass signal. And I would say that the value of this capacitor is very impactful as far as where, how much high-end content you have, because again, this is going to be multiplied through the circuit with the generation of harmonics. So, if you increase this value, again, it's opposite. So if you increase this value, you're going to bring this line up higher and higher. That means that less high-end signal is going to be attenuated and more of it's going to pass through. So you increase this capacitor, you're increasing treble. Check the other sources on that, but this is an interesting capacitor. I do think this is a key point in the voicing of this circuit, and this capacitor exists at every one of these three gain stages. So you could bump it up to 560, or you could bring it down to like 330. Those would be some pretty meaningful tweaks in the tone of this overall circuit. So the negative feedback loop is really interesting in how they implement it here. Okay, then we've got this 10K resistor is going to help regulate the 9 volts coming from our power supply going into the collector. That's pretty standard. Got another coupling capacitor here. Now we've got a sustain pot. Now up until this point, right in about here, we're really just dealing with kind of a modified LPB1 booster. And so it's interesting that the gain control is really setting the level of that amplifier before we move through the rest of the circuit. Okay, so now we're going to move to the clipping amplifier section. Again, there are two of them. They're both pretty much the same, and for the most part they're similar to what we saw before. We've got our biasing resistors here and here and here. We've got our negative feedback loop right here. But now we add two diodes and a capacitor. Now the capacitor is coupling in the same thing that we saw before, but it's really just serving to couple the clipped, like the DC from the clipped signal from going through our negative feedback. Not super critical, but these diodes I think are what I really want to highlight. And first of all, I want to highlight that with clipping diodes, the position of them here, they're in the negative feedback loop, right? Because the signal is coming through here, and this point, and this point are all connected. There's no resistors or capacitors in here. So we're in the negative feedback loop, which is fascinating because that is indicative of soft clipping, similar to what you would actually see in a tube screamer. So this portion of the circuit, the clipping portion, is very, very similar to what you would find in a tube screamer, rather than like a fuzz face, which clips the signal in a radically different way. So it's very interesting to me that a big muff is a fuzz, when in reality the clipping is soft clipping. Because we're in the negative feedback loop, the effect of these clipping diodes is diminished. So if you think about our sine wave, what we mean by soft clipping is that this is going to be our center line. I have another video on diodes, so go and check that out. You get a forward voltage line, which maybe is right here. So that means anything that peaks above that line. We've got two of them. So this one here is going to take the top. This one here is going to take the bottom. So any part of the signal that passes over the forward voltage line gets clipped off. Now it's soft clipping though. So what that really means is, a hard clipped signal would just chop it, straight line. But a soft clip, again, because we're in the negative feedback loop, the effect is kind of diminished a little bit. It just kind of rounds it a little bit. So the knee of the, there's a little bit of a curve here, and contrasted with a straight line, we've got a little bit of a knee. So that softens the effect. And ultimately what that's going to do is, it is going to reduce our dynamic range, because the loudest point, we used to be here and here, has now been squashed down. So our overall level has actually decreased. And it also is, this clipping action is also going to generate harmonic distortion. And so the interesting thing though is we've got two of these cascading into one another. So remember we amplified our signal here, and let's draw that out. So let's say that our input signal was this guy here in red. This is from the guitar. Okay, it goes through this first gain stage. So the net result of this first gain stage is simply to boost up the signal. It's a pretty, straightforward copy of its former self, just a little bit louder. Well, now we took that louder signal and now we've clipped the peaks. So we've generated some distortion. We've also reduced our dynamic range and our overall output level. And actually we've done that twice. So if the first time it clipped it like here in blue, the second time it's going to clip it like here in red. And it's going to be even harder. I'm not really conveying it very well with my drawing, but it's going to be more of a hard clip. Two soft clips kind of creates a hard clip. And our overall output level has diminished by a fair bit. Maybe not quite as low as it was at the start, but definitely a lot lower. And so, running it through this first clipping stage and then into the second clipping stage, we've really pretty drastically changed the tonality of our signal. So now let's go to this tone stage. Now this tone stage I think is really interesting because what you basically got is two filters. Now there are two types of filters. There are resistor capacitor filters and there are capacitor resistor filters. So if we examine that, you can see we've got a capacitor and a resistor. That's our CR. This is allowing high frequencies to pass, whereas over here we've got our resistor and our capacitor. That's our RC. That's going to allow low frequencies to pass. Because again, our signal comes into this point. The high frequencies that are above the cutoff point of this capacitor will pass through freely, and the rest of the signal, the lows, will go through this resistor. Then these high signals, depending on the resistance, will either bleed to ground or be allowed to pass through. And likewise over here, the rest of these low frequencies, they'll go through here. The highs are bled to ground, because again our highs are already coming through over here. And then the rest of the low mid-range, again, passes through the tone depending on the position of this, the resistance of this pot. Now, one thing that's really interesting about this tone stack is it really, let's draw the frequency response. So we've got our RC filter that's letting lows pass. Then we've got our CR filter that's letting highs pass. And you end up with this dip right here. And that produces the very prototypical mid-range cut that you would associate with this circuit. And I would say that this is one place where you can do a lot of experimentation, and I may do a follow-up video on the type of mods that I choose, but you can really put any type of tone stage stack that you want here. I know that this resistor right here, I think that you can turn it into a pot, a variable resistor, and that will actually become more of a mid-range control. And I also know you kind of do a lot of wild things with this stage, and I'm probably going to look into doing that. But this tone stack here is really a critical place that the overall signal gets shaped for that mid-range cut that the Big Muff is so familiar with. Okay, then lastly, we've got an output booster. Pretty straightforward. Now there's no negative feedback in here. So it's just a very simple, straightforward boost stage into our output volume control. So that's an overall look at the circuit. Now I've got the Russian Big Muff, and I would say that the characteristics of that are going to be, like these capacitors are going to be a little bit lower value, which will mean, so for example, if this is at 470 or even 330, that means it's going to attenuate the highs a little bit more for a little bit of a darker, woollier fuzz. We've got pretty full frequency with these coupling caps, so definitely contributing to that darker sound. And then really the main thing is going to be the type of transistors that are used. I believe my circuit has 2N5088s or 89s, I'm not exactly sure. But those are pretty high output transistors, so it's going to be a lot of gain, and hopefully a really fun build. So I hope you guys enjoyed the look at the schematic and the circuit, and we're going to get into building it here pretty soon. But this gives us a roadmap of where we're going to go and the type of modifications we're going to look at, and it should be a lot of fun. Thanks. Bye.